Hi chemistry students, welcome back. You performed a number of inquiry activities to see how pressure, volume, and temperature related to each other, and we're going to be more mathematical about it today, and this will draw on your algebra skills. These are collectively called the gas laws, and it allows us to calculate one variable given the others. So let's go through that. We are going to look at three of them today. That is Boyle's, Charles, and the combined gas law. And first of all, let's look at Boyle's. Boyle's law relates to pressure and volume. And a good way of looking at that in your book here is your bike pump. So you are familiar with easing the pressure on your bike pump by lifting up on the handle, and that increases the volume. And then when you increase the pressure and push down, the volume inside of the bike pump is small. And this is exactly what you saw yesterday when you went and put the balloon in the flask and you reduced the pressure, the volume went up. Or alternatively, on the first activity that you did where you put the masses on the syringe and found that the more mass you put on it, the smaller the volume in the syringe. This is the same idea of Boyle's law. Boyle's law says that pressure and volume are indirectly related. Here's an image of what you did yesterday. You put masses on top of a syringe. See these green masses? If we put more and more mass on it, the volume goes down. The plot that we did, we used mass on the x-axis, but it is directly related to pressure. As pressure increases, volume decreases. A graph with this kind of shape is an indirect relationship. As one goes up, the other goes down. This is Boyle's law. All right, so let's try to put that into a formula. It says pressure times volume is a constant, or P1V1 equals P2V2. Here's a sample problem, and you should have a worksheet that you can follow along. A submarine has an internal volume of 12,000 liters. That's V1. What will be the volume of the gas? Okay, I'm looking for V2. When the pressure goes from 1 atmosphere, that's P1, to 1.4 atmospheres, that's P2. So P1, V1 equals P2, V2. I'm looking for V2. So it's your preference how you want to do this. If you want to put the numbers in first or rearrange the algebra. I usually rearrange the algebra, P2, and I put my numbers in. 1, my volume is in liters, so my answer will be in liters, and this is 1.4 atmospheres. And I should have written atmospheres here, but my atmospheres cancel and I'm left with liters, and this turns out to be 8,571 liters, but I only have 2 sig figs, so I'll say it's approximately 8,600 liters. There you go. That's your first Boyle's law problem. Next problem. An engine piston contains 56 milliliters of gas. What is milliliters? Right, that's V1. At a pressure of 1.5 atmospheres, that's P1, and it is compressed to a volume of 48 mils, that's V2. What will be the new pressure? I'm looking for P2. So, P1, V1 equals P2, V2. P2 will be P1, V1 over V2. Put in my numbers, and I'll have P2 equals 1.5 atmospheres, 56 mils over 48 mils, and I'll come up with a new pressure of 1.75 atmospheres, but it's approximately 1.8 given that I have 2 sig figs. Charles' law relates volumes and temperatures. Yesterday you had the flask with the balloon on the top, and you heated up the flask and the balloon swelled, and then you put it on ice and the balloon shrank. This is the relationship between volumes and temperatures that is described by Charles' law. An animation of Charles' law is seen here. We have a piston that's heated. The piston's free to move. As the heat's applied, the gas molecules increase in energy and push against the piston and raise it up. The volume increases when temperature increases. This is because the gas molecules have increased energy and push up on the piston. Volume is directly related to temperature. A direct relationship is a straight line plot that increases to the right. As one increases, as temperature increases, volume will increase, or vice versa. Let's do two Charles' law problems. I have 130 liters of gas. That's V1. In a piston at a temperature of 250 degrees Celsius. In gas law problems, you immediately switch to Kelvin. To get to Kelvin, this will be 523 Kelvin. The reason we have to be in Kelvin is we may not divide by 0. If I cool the gas until the volume decreases to 85 liters, that's going to be V2. What will the temperature of the gas be? So I'm looking for T2. So V1 over T1 equals V2 over T2. And what I'm looking for is right here. So rearranging the algebra, I get T2 is V2, and it's the flip of this, because I'm bringing T2 over here, and then I'd be multiplying by the reciprocal of this. So it's going to be T1 over V1. Check the algebra out if I lost you there. So V2 is 85 liters, T1 was 523, and V1 was 130. And the new temperature, when this piston has been pushed in, is 342 Kelvin. But keeping sig figs, we'd say 340 K. Okay, and just take a moment and think about it. The temperature went down when the volume went down. Does that make sense? That's what we say. We say that there's a direct relationship, so they are in truth changing in tandem. Next problem. I have 58 liters of helium in a balloon at 35 degrees C. Okay, you're given your V1 and your T1, and let's just convert that right away. T1 equals 308 Kelvin, adding 273 to this. We increase the temperature to 65. That's 338 Kelvin. What will be the new volume? You're looking for V2. So V1 over T1 equals V2, what I'm seeking, over T2. Solving for V2, we'd have V1 over T1 times T2. And you get 58 liters, 338 Kelvin over 308 Kelvin, and we see it as 63.6 liters, but maintaining sig figs, we'll say it's approximately 64 liters. Does that make sense? That the volume increased when the temperature increased? Yes, that makes sense. And you should always cross-check yourself when you work gas law problems. I'm going to briefly mention Gay-Lussac's law, which relates pressures and temperatures. It says that pressure and temperature are directly related, and the best way of looking at this is through the PhET animation shown here. And we can measure the temperature here. We can increase the pressure by pushing this little guy on the left, and I can introduce gases by pumping the handle and putting some gas molecules in here. So let's fill the chamber with gas. And now I'm going to increase the pressure and watch the temperature on the top right. So when I push in the piston, the gas molecules are forced to exist in a smaller space, and they will have more energy inside the smaller space, and it's going to be seen as a rise in temperature. So pressure and temperature are directly related. I think the more obvious thing, reset this, put gas molecules in here, is our experience in putting soda cans in campfires. I don't know if you've ever done this, but you are familiar. If you'd put a can of soda in a campfire, put it under heat, we would see the man on the left, he's working so hard to keep the gas molecules inside, but eventually it blows the lid and it explodes. It's easier to envision this relationship of Gay-Lussac's, that pressure and temperature are directly related. If you think about temperature going up, it's easy to think of pressure increasing. Less intuitive, less in our experience, is increasing pressure leading to an increase in temperature. But we're saying these are directly related. So Gay-Lussac's law is stated as pressure and temperatures are directly related. We're going to wrap that up with Boyle's and Charles' law to come to the combined gas law, which says P1V1 over T1 equals P2V2 over T2. This allows us to be changing multiple parameters. We could change volume and temperature and measure or predict the change in pressure and vice versa. So you'll recognize these problems as being ones that are more wordy. They have more data in them, and it helps you identify the ones that are the combined gas law. So here are two combined gas law problems on your worksheet. First of all, notice that they are indeed more wordy. You have more numbers in them, and that's the biggest clue that a combined gas law is required. Get into the habit of recognizing your units, and it will make these problems doable. It's actually helpful to maybe create a table with all of your various values on the side. And we could do it this way. All right, so a toy balloon has an internal pressure of 1.05 atmospheres. Atmospheres is a pressure unit, so that must be my original pressure. And a volume, straight up given to you, as 5 liters. If the temperature where the balloon is released is 20 degrees Celsius, so this would be my T1, and I immediately convert it to Kelvin, so 273 plus that is 293. What will happen to the volume? All right, this is what I'm looking for, the new volume. When the balloon rises to an altitude where the pressure is 0.65 atmospheres, okay, that's my new pressure, and the temperature is minus 15. So 273 minus 15 is 258 Kelvin. Well, your combined gas law is P1V1 over T1 equals P2V2 over T2. What am I looking for? This guy. Okay. So your preference, I like to rearrange the algebra, and so before I plug numbers in, I want to rewrite this as the left side is still intact, but I'm going to be multiplying by the reciprocal T2 over P2. Check your algebra if you're not in agreement on that. That becomes this, isolating my V2, my variable, and now I can plug in all of my numbers. 1.05, 5 liters, 293, over, that's the wrong temperature, isn't it? T2, 258 Kelvin, and then T1 is the 293. And my P2 is 0.65 atmospheres. And on your calculator, you'll do 1.05 times 5.0 times 258, enter, divided by parentheses 293 times 0.65, close parentheses. When you do all of that, you should end up with a volume of 7.1 liters. That's your answer. So just looking back over this problem, Creating a table is a helpful way to keep your variables straight. You'll become more and more adept at associating the variables with the units. And then it's algebra manipulation to isolate your variable of interest, plug in the numbers, solve. All right, next problem. A bag of potato chips is packaged at sea level where the atmosphere, it's 1 atmosphere, and the temperature is 25 degrees C. So P1 is 1.00 atmosphere. T1 is 273 plus 25, which is 298 Kelvin. And V1 is my original volume of the potato chips, which is 315 milliliters. Now you're allowed to stay in milliliters. Just remember that your new volume that you're looking for, because again the question here is what is the new volume, will be in milliliters, not liters, when you're finished. Okay, what's my next data? If this bag of potato chips is transported to Denver, where the pressure is 0.775 atmospheres, and the temperature is 20, what is the new volume? Well, we already have this rearranged here. It's the same, right? V2 will be P1 V1 over T1 times T2 over P2. And that will be 315. Remembering my answer is going to be in milliliters. T2 is 293. T1 is 298. And P2 is 0.775. When I do 1 times 315 times 293, enter, divided by parentheses 293 times 0.775, close parentheses, I get 400 milliliters. And I'm going to draw a little line over this 0 because I have 2 sig figs. So I'm trying to communicate that this one counts. So 2 sig fig answer, 400 milliliters. That is the combined gas law. Using lots of data to get your answer, it merges all the ideas of Boyle's, Charles, and Gay-Lussac's laws.